Sorry for the interruption, participants. Okay, let us start with the topic now. In today's lecture, you are going to learn about the vectors in n-dimensional vector space and the vector spaces, subspaces of the vector spaces. Then you will learn about the spanning sets and linear independence and basis and dimension. And finally, we'll learn about how to find the rank and nullity of a matrix. So these are basically the topics on which we will discuss today. So as all of you know that linear algebra is the mathematics of vectors and matrices, and we make use of such vectors and matrices since these are the convenient mathematical way of representing large amount of data. So in data science or in most of the fields, the data is represented in terms of the matrices. And the field of data science leans on many different applications of linear algebra due to the representation of the data in the matrix form. So a good understanding of linear algebra really enhances the understanding of many machine learning and deep learning algorithms. In the matrix form, as we know that in the matrix form, the data is organized in rows and columns. And so it proved to be a convenient way to represent the data. And so that is why in the data science or in machine learning, it is used to represent samples with different attributes in a compact form. Linear algebra provides us tools to understand and manipulate matrices to derive useful knowledge from this data in the matrix form. So now let us start with vectors first. First, we'll learn about the vectors, which is a part of matrices only, and then slightly we will go towards the matrices. Okay, so till now you might have seen a vector of this kind. A vector in a plane is expressed by a directed line segment whose initial point is generally in origin and whose terminal point is this point x1, x2. So this is the geometrical way of representing the vector. But here we will represent our vector not in the geometrical way and like this arrow. It will be represented in the algebraic form using this pair of this representation. Okay. So let us say if you have you want to represent a vector which is in the one dimension, then that is nothing, just the numbers, real numbers itself. And if we represent the vector in the two dimension, then this is a point x1, x2. Similarly, if we are in the three dimensions, you see that in case of the three dimensions, we have this x-axis, this x-axis, then this y-axis and the z-axis. So if a point is represented in the three-dimensional space, it will be represented like this, x, y, and z. Or also you may write it as x1, x2, or x3. So there will be three components associated with this vector. One is for the x-axis, another is for the y direction, and the third one it represents in the third direction, z direction. But we not only expand these vectors in two-dimensional plane or three-dimensional space, but using the linear algebra, we usually represent or we usually think of the vector in an n-dimensional space. So in the n-dimensional space, any vector is written as an n-tuple of components here, say, which are called the coordinates. So an n-tuple, some vector, let us say you have a vector u. This will be represented in this form, x1, x2 up to so on, xn. It will have the n components here. And so this n tuple can be viewed as a point in n-dimensional space. This n represents its dimension, and this r said that we are in the real numbers with the xi, z as its coordinates. So this n tuple can also be viewed as a vector x, this vector which is written in the bold. This bold represents a vector x. This vector x has the components or the coordinates x1, x2, and so on up to xn because it is in the Rn space. as I told you, if we represent this any vector in R1 space, then that is a set of all real numbers. In R2 space, this is a set of all ordered pair of real numbers, x1, x2. If we represent it in the R3 space, then that is a set of all ordered triple of real numbers, x1, x2, x3, and so on. For n equals to 4, that is in the R4 space, it will be an ordered quadruple of real numbers, x1, x2, x3, x4. Similarly, if we go for the Rn space, then obviously it will be x1, x2, and xn. Now let us learn about the algebra of vectors. Say you have two vectors, vector u and vector v, and with the components u1, u2 up to un and v1, v2 up to vn. Then these two vectors will be called equal if and only if each of the corresponding components of the two vectors is the same. And the second thing is that they should have the same number of components. That if u is having n components here, then we should also have n components or coordinates here. So for u and v to be equal, u1 should be equal to v1, u2 should be equals to v2, and so on. The last element un should be equals to the vn. Similarly, we can define the vector addition in this way. U plus v, the addition of two vectors, is defined by
Hello, ma'am.
Adding the corresponding coordinates of the two vectors. That means the first coordinate u1 is added to the first coordinate here, u1 plus v1. That will give you the first coordinate of u plus v. So here we have u1 plus v1, then u2 plus v2, and last un plus vn. And similarly, we can just explain this scalar multiplication. This c is a scalar. A scalar is nothing but a real number. Okay. So this scalar multiplied with this vector will give you this c, this scalar multiplied with each and every component of this vector u here, and that will give you the new vector c into u. So the sum of the two vectors and the scalar multiplication of the vectors in Rn are called the standard operations. So these two operations, vector addition and scalar multiplication, these two are generally called the standard operations in Rn. You can also define the difference between the two vectors just by taking the difference of the corresponding coordinates, and then we define the zero vector. This zero vector, if we define the zero vector in two-dimensional plane, in R2, then this zero vector will have two components, two zeros here. And if we define the zero vector in R3, then it will have three coordinates. Similarly, you can define zero vector in Rn, then it will have n components or n coordinates here. So this depends upon the situation in which space we are defining this zero vector, and accordingly we will have its structure. These are some practice questions which you can do. You can easily find if you have been given u, v, and w as three vectors, then you can easily find this x by making this using this scalar product, and then the vector here scalar product also, and then vector addition and vector subtraction. So these can be easily done. It's a simple algebra. Now next we have this important function, which is the norms. So norm is a function which actually defines the length of any vector. Okay. Usually we define the norm with this formula, and the norm is written in this way. This is the vector x, these two parallel lines alongside x, and this p defines what kind of norm it is. Okay, so this is called the LP norm. In some books you will see it as small LP, or it may be capital LP, that doesn't matter. So this is the LP norm. It is defined like this, and the formula for the LP norm is this is equals to, if we have x vector having the components x1, x2, and so on up to xn, then this norm of xp will be x1 raised to the power p plus every component having the power p and added together, and finally we have the 1 by pth power here. So every element of vector x is raised to the power p, then their sum is raised to the power 1 by p. or in the simplified form with the summation form, we can also write it as this is equals to summation xip with I varying from 1 to n raised to the power 1 by p, as it is written here. So norm can be defined in this way also. Now for this LP norm, three norms are defined according to the value of p, according to the p. If p is equals to 1, we define the L1 norm. If p is equals to 2, we define the L2 norm, and similarly we also define the L infinity norm. So these three I'll explain here. The first one is the L1 norm, which is generally called as the Manhattan distance. Okay, so this norm is defined according to the Manhattan distance, because when we define the L1 norm, the formula for the L1 norm becomes, if you see there, this is nothing but the distance. Means distance is measured in the blocks only. So L1 norm is called the is measures distance between 2 points such that you can only travel along orthogonal blocks. So if you want to measure the distance from 0, 0 to 2, 3, or this vector 2, 3, if you want to measure its distance, then you will have to go along the x-axis, then along the y-axis. So this total distance will be measured here, which is nothing but the modulus of whatever is here. Let us say you had the vector -2 and 3, then you will take the modulus of both the vectors, modulus of -2 plus modulus of 3. Now because we are taking p equals to 1, so it will be raised to the power 1, and outside also we will have 1 by 1, that is power 1. So this is nothing but modulus of 2 plus modulus of 3, and that is equals to 5. Similarly here, because we were having this point as 2, 3, its L1 norm will be defined to be modulus of 2 plus modulus of 3 raised to the power 1, and which is equals to 5 also. Then similar way you can define the L2 norm, which is called the Euclidean norm. In L2 norm, we will have the formula according to the LP norm formula, where we will have the formula for L2 norm as under root of, or you can say as x1 raised to the power 2 plus x2 raised to the power 2 if you have a vector, say 2 comma 3, this is x1 and this is x2, so it is x1 square plus x2 square whole raised to the power 1 by 2, or it may be written as under root of x1 square plus x2 square. So that is what we have done here to find the norm of A. Second norm, L2 norm of A, we will have the under root of x1 square, that is 2 square plus 3 square. 2 square plus 3 square is 13, 4 plus 9. So this is under root of 13, that is your L2 norm. So L2 norm is the shortest distance between the 2 points. So if you want to find out the L2 norm of some point, you will find out which will be the shortest distance from origin to this point. So that is this point, and obviously we know that this is nothing but this is square plus this is square, it's under root 2 square plus 3 square under root. So that is why the Euclidean norm is defined in this way. Then we define the infinity norm, which is just the maximum absolute value of the given vector. Okay, so that is why this infinity norm is equals to 3 here. So here I summarize those points. Say you have the vector x here. You have the vector x here. Then the L1 norm is defined in this way. Okay. We have the L2 norm defined in this way, and the L infinity norm is the maximum value of modulus of x1. So among the modulus of x1, whichever is the maximum value, that will return the L infinity norm here. Now let us again move towards the vector and just go towards this little bit theory about what is the linear combination of vectors in Rn. In this whole lecture, we will always remain in the space of Rn. Means our vector will always be in the n-dimensional space with, let us say, this vector, and its components will be from the n dimension. So we will have here n components of this vector x1, x2 up to xn. Okay. So let us look about what is the linear combination of vectors. So a vector, let us say we have some vector x. This vector x is called a linear combination of some other vectors v1, v2 and vn. If we are able to express this vector x as a combination of these vectors in this way, that means we can write x as a combination of v1, v2, vn by writing it as c1 into v1 plus c2, v2 plus up to cn into vn, where these c1, c2, cn are nothing but the scalars or real numbers. So if we are able to find out some values, some finite values of these scalars, so that this x is equals to c1 v1 plus c2 v2 up to cn vn, then we will say that x is a linear combination of the vectors v1, v2 and so on vn. Now look at this with this example, then it will be more clear to you. So you have been given one vector x. This vector x, you have to find out whether you can write this vector x as a linear combination of the given vectors u, v and w. Then what is our aim here? Our aim is to look whether we can write x as a linear combination of these three vectors, or we are able to write x as equals to, or you may write it as in, if you want to write in terms of c1 c1 c2, then this may be written as c1 u plus c2 v plus c3 w. So if we are able to write this vector x as a combination of this kind, then we will say that x is a linear combination of the vectors v, u, v and w here. So for that, what we have to do, because we know x, vector x is our -1, -2, -2, and this is equals to, because we have to find out c1, c2, c3, so c1 will remain here. Our vector u is given, which is 0, 1, 4. Then we have already been given the vector v, which is -1, 1 and 2, and our vector w is 3, 1, 2. Okay, so now if we use the scalar multiplication here, then these scalars will go inside the vectors and it will give us c1 into 0, that will be 0, then c1, then 4c1 plus minus c2, c2, 2c2 and plus 3c3, c3, sorry, this is comma, and 2c3. And if you use the vector addition here, you can add the corresponding components of all the three vectors. This will be 0 minus c2 plus 3c3. So this will be minus c2 plus 3c3. Then c1 plus c2 plus c3. The second components will be added, c1, c2, c3. And then we will add the third components, 4c1 plus 2c2 plus 2c3. Okay, so here in this right hand side vector you have the three components, and also you have the three components in the left hand side vector. So these, as these two vectors are equal, that means their corresponding components should be equal. So it means that, or it implies that -1 should be equals to minus c2 plus 3c3, then -2 should be equals to c1 plus c2 plus c3, and again the last component, which is -2, it should be equals to the last component in the right hand side, that is 4 c1 plus 2c2 plus 2c3. So here you get these three equations in place, because in the question which is written here, we have used a, b and c, that is why this c1, c2, c3 are written as b, this is a, b, c here. So you can write in this form also. Now our aim is to check out whether we are able to solve these three equations in three unknowns. Three unknowns are a, b and c here. So we have to solve these three equations in three unknowns so that we get some finite values of all the three variables here, this a, b and c. So if you, I think everybody knows how to solve the system of linear equations. So this is a system of linear equations which can be easily solved to get the values of a, b and c. And if you solve it, you will finally get the values of a equals to 1, b equals to -2 and c equals to -1. Now, as you got some finite values of a, b and c here, you are able to write the vector x by putting the values of a, b, c in this and get this x as a linear combination of these three vectors. If somehow we are not able to get the values of this a, b and c by solving this system of linear equations, then we will say that we are not able to write this vector x as a linear combination of the given three vectors. Okay, so if we are easily able to get the values of a, b, c, then it is all right, and we are able to write the vector x as a linear combination of the three vectors u, v and w. Next, we have the vector spaces. What is a vector space? As you have a space here, let us say we have a set of some vectors. We have a set capital V where so many vectors are there. Okay, so many vectors are inside. All the dots are actually the vectors inside the V. Fine. Now this set of vectors V with some operations defined on it. Here you see that this has the structure. This is the structure in which this set of vectors is defined, which is V. And then we define this vector addition on V. And this is the scalar multiplication on V. So if we define the vector addition and scalar multiplication on the vectors of the set V, then this set is called a vector space if it satisfies these given 10 properties, which are also called the 10 axioms. So if those 10 axioms are satisfied by the vectors of this set V, then this set V will be called the vector spaces. And also it should be very clear to you that this scalar vector addition and scalar multiplication should be defined according to the given conditions here, and that should be taken care of. So let V be a set on which two operations, addition and scalar multiplications, are defined. If the following 10 axioms are satisfied for every element u, v and w in V, u, v and w are nothing but the elements or the any arbitrary elements from the vector from this set V, and every scalar is a real number, and let us say we have taken two scalars here, C and D, then V will be called a vector space and the elements in V are called the vectors. So let us look at these 10 axioms. The first one is this: u plus v should be in V. So for any two arbitrary given vectors, say I have taken this vector u here and I have taken arbitrarily some vector v here. If we add these two vectors, then their addition u plus v should also be somewhere inside this set V. Okay, this property is called the closure property or the closure with respect to the addition. So we say that the V is vector space, vector V is closed with respect to the addition. And then second property is that u plus v should be equals to v plus u. This property is called the commutativity. Commutativity. Third is that u plus v plus w, if we add v plus w first and then add u, or if we add u plus v first and then add w to it, then those things should be equal. This is called the associativity. So if given set of vectors is closed with respect to addition, it is commutative, it is associative. And the fourth property is that there should be a zero vector inside V. There should be some zero vector inside V according to its dimension, such that if we add any of the vectors from this set V, then to 0, then that vector remains the same. So if you add u plus 0, this 0 may be defined according to the condition, and that is why it is called the identity. So because we are defining plus as a usual addition of this real numbers here, so our identity will remain 0 in this case. So if u plus 0 should be equals to u itself, and this is called the existence of this property, or this axiom number 4 is called the existence of identity. Identity in this case is 0 vector. The fifth property is that for every u in V, there is a vector in V denoted by minus u such that u plus minus u is equals to 0. So whenever you add u to minus of u, you should get the identity element here. So this property is called the existence of inverse. That means there should be an inverse associated with every vector so that if you add them, you should get the identity element. So these were the 5 properties related to the addition here. Next, we have again the 5 properties which are related to the scalar multiplication. And the first property here is that if you multiply any scalar with any of the vectors, then whatever you get Cu, that should also be inside the V. C into U plus V should be equals to Cu plus Cv, and then C plus D into U should be equals to Cu plus Du, where these C and D both are the scalars. Similarly, if you multiply in this way, first multiply this scalar D with U and then multiply with C, or first you multiply these two scalars and then multiply with the vector, both the things should be the same. The last property is this one. Although it looks very trivial, but it is very important property, that 1 into u should equals to 1. So this 1, if multiplied to any of the vectors inside the set, it should give you the same vector again. Now here again we had the 5 property. The first property here, that is called the closure property, or we say that the V is closed with respect to the scalar multiplication. Okay, so in the closure property we have 2 properties. First is the closed, the vector space, this set V is closed with respect to addition, and set V is closed with respect to the scalar multiplication. These two are the closure properties. So whenever we have given any set V with plus n multiplication defined on them, and if all the 10 properties are satisfied that with that set, then we say that this set is a vector space. Now this everything is written in short here. Vector space consists of 4 entities: a set of vectors, a set of real numbers which are scalars, and 2 operations. 2 operations were addition and scalar multiplication. Then V was non-empty set of vectors, C are scalars. Then we have defined addition, and this is called the vector addition. This is called the scalar multiplication. And then V with these two, vector addition and scalar multiplication, is called a vector space with the 10 axioms which should be satisfied. So the set V together with definition of vector addition and scalar multiplication satisfying the above 10 axioms is called a vector space. Now some examples of vector space are given here. You see that every set of vectors given to you with addition and scalar multiplication defined on them may not be a vector space. So we will look at one example here which is not a vector space. So to show that a set is not a vector space, you need to only find one of the axioms which is not satisfied by that set of vectors. So as it is given here, let us say you have been given V, some set V have been given to you. This V is equals to, this is a set of integers. Okay, so because this is a set of integers, its elements will be of this kind. It can be negative integers, 0, positive integers, and so on. So any integers will lie inside this set. Then we have to prove that this set is not this set of vectors, which is the set of integers, is not a vector space. This we have to prove. To prove that, we will have to find out among the 10 axioms one or more of the axioms which are not satisfied by this set of vectors. So it is very easy to see that the scalars which we have in case of the vector spaces, the scalars we have are the nothing but the real numbers. So, okay, so all the scalars are real numbers. Now we can think of one of the property. If you very carefully see that, let us say any number you take from the set of this integers and you multiply, you do the scalar multiplication, as we define the scalar multiplication of C into U, that should be what it should be? It should also belong to the set of vectors V. But in this case, if you take this scalar as, let us say, 1 by 2, and some vector, any vector you can take from this, or because this vector is a number here, so any number you can take. Let us say I take the number 3. Okay. Then this 3, if you multiply 1 by 2 with 3, you will get 3 by 2, which is a real number. So it will not belong to the set of this vectors here. Why? Because this is a real number, and this set of vectors V, that is having only the integers inside this. So it will not belong to this V, and that is why, because this multiplication with respect to the scalar C is not closed here, and so we can say that this property is not satisfied by the set of integers. So it is not closed under scalar multiplication, and that is why, because this property is not satisfied, and so this given set of vectors, which is the set of integers, is not a vector space. I hope this is clear to everyone. Similarly, you can have some other examples. You can look at the examples afterwards. Next, we have the subspaces of a vector space. So previously, we were in a bigger set here, which was our vector space. In this vector space, we had defined vector addition and scalar multiplication. And inside this vector space, we had so many vectors. Okay, so many vectors are there. Infinite number of vectors are there with some properties satisfied by them. Then we take a non-empty subset of this set, vector space V. And so because this is non-empty, that is why it is written this W. Let us say we take the subset of this vector space. W is nothing but that is a subset of this vector space V, or it can be at the most equal to the V. And this W is a non-empty set. Okay. Then this non-empty subset W of V is called a subspace of V if W is a vector space itself. So if W is also a vector space, under the same operations of vector addition and scalar multiplication as we defined on V, then W is called a subspace of V. So any subset of this vector space we take, this subset is this W, okay? And this W also satisfies all the properties of vector addition and scalar multiplication, which is defined on the vector space V. Then this W is called the subspace of V. Now you see that for every vector space V, this zero vector is a vector space, and it is a subspace of V always. And similarly, the vector space V itself is always a subspace of the vector space V. So these two spaces, or these two subspaces, are called the trivial subspaces of the vector space. So these are called the trivial subspaces of. Why they are called trivial? Because we don't need to just justify whether they are subspaces or not. We don't need to just check them whether they are subspaces. They are always the subspaces of the vector space V. So that is why zero vector and vector V itself are called the trivial subspaces of the vector space V. And any subspaces other than these two are called the proper or non-trivial subspaces of vector space V. Then let us now here how we will examine whether the given subset of a vector space V is a given subset, say as we were having here. Say we have the vector space V, and there is a subset of this vector space, which is W. If you want to check out whether this subset is a subspace or not, subset is subspace or not. So for that, we don't need to check so more properties of subspace or vector space. We'll need to check only the two properties, which are the closure conditions. What were the closure conditions? The closure conditions were our vector addition and scalar multiplication. So if you will check whether the vector addition and scalar multiplications are defined on W, then we will say that W is a subspace of V. So test whether a non-empty subset being a subspace. If W is a non-empty subset of a vector space V, then W is a subspace of V if and only if only two properties or only two conditions should hold. The first condition is that whatever vectors U and V you have in W, you can take U and V, any arbitrary vectors in W, and then their sum should also be in the W. And second is that if we take U any arbitrary vector from W and C is any scalar or any real number, and if we multiply them together by the property of scalar multiplication, then this C into U should also be in W. So if these two properties are satisfied, then we will say that W is a subspace. You don't need to check the other properties of a vector space. And also you should understand that this subspace is also itself is a vector space. So this subspace, which is a subset of the vector space V, itself is a vector space. So this is the proof. You can go for the proof if you are interested. You can look here. Then we have next this theorem. The intersection of two subspaces is always a subspace. So I will not go into the details of this. You should just remember that if we take the intersection of two subspaces, then whatever we get, let us say we have two subspaces. We have a vector space V here, and its two subspaces are U and W. These two are the subspaces, and if we take the intersection, then this intersection is also a subspace of V. But in case we take the union of these two, union of U and W, then that is not a subspace, as it is written in the end here. The union of two subspaces is not a subspace of a vector space. Again, if you are interested in the proof, which I don't think is needed for you people, but if somebody is interested, he can go through this proof here. Now, next we have the another very important concept related to the linear algebra, and it is very useful for the data science people also. That is the linear independence. And associated with linear independence, we have another term which is the spanning sets. So these two things let us learn. So first, this I have already explained you the linear combination. Linear combination, you have already known that a vector U in a vector space is called a linear combination of other vectors, some other vectors U1, U, as it is given here, V1, V2, Vk. If U can be written in this form, this you have already seen that if you are able to write U in this form as a linear combination of the vectors V1, V2, and Vk, then this is called the linear, you will call the linear combination of the vectors V1, V2, and Vk, where C1, C2, Ck are the real numbers or the scalars. Finding the linear combination, this one example we have already done. If you need another, some more example, this example is given here. You can go through or you can try it yourself and then check whether you are doing it correctly or not. Again, we have the same linear combination here. Next, we have what is the spanning set, the span of a set S. Let us say you have been given some set S. This set S has the vectors in it, V1, V2, and so on up to Vk. That means k vectors are there inside this set of vectors set of vectors S. This S is a set of vectors in a vector space V. Then the span of this set, span of S, is the set of all linear combinations of the vectors in S. So all possible linear combinations of these vectors, if we take, then we can write their linear combination as C1 V1 plus C2 V2 plus and so on Ck Vk, where we take these C1, C2, and Ck arbitrary numbers. Okay, so if those will be arbitrary numbers, then all the linear combinations will be there in this set span of S. So span of S is containing the set of all possible linear combination of vectors inside the S. So this is called the spanning set of S or the span of S. So if every vector in a given vector space V can be written as a linear combination of vectors in a set S, then S is called a spanning set of the vector space V. So I think this term is clear, and here it is written that we can define span of S in so many ways. Span of S is also called the generator of S, or we can also just state it as S spans V. We can also state as S generates V, or V is spanned or generated by S means S is a spanning set of V. So these statements are equivalent. You can use any of them according to your wish. Now let us look at here. Say you have one example, we will look here. Let us say you have the set S. This set S has three vectors, vector U, vector V, and vector W. Our vector U is nothing but 1, 0, 0, 0, 1, 0, and 0, 0, 1 is the vector V. Now we say that this set S spans R3. Okay, R3 is the three-dimensional vector space because any vector u1, u2, u3 in R3 can be written as, we say that S is a span of this R3. Okay, we say that S spans or generates the vector space R3 if any vector in this, any vector u which is inside R3 can be written as a linear combination of vectors in this. So we will have to take some other vector in place of u, x, because we are taking the vectors inside S as the vectors u, v, and w. So if we are able to write any general or any arbitrary vector x in R3 as a linear combination of these three vectors, then we will say that this set S, which is having the vectors u, v, w, is a spanning set for the vector space R3. So you see that if you have the vector space, any vector space, in this case this is R3, and then you have a set here S, okay, which is having only three vectors u, v, and w. You see that these three vectors will generate all the vectors inside this vector space. So that is why we call it as the generating set or the generator of the vector space R3. So you will have to check by writing u equals to, you see that you will have to write this u as a linear combination C1, U1, sorry, this u, I have taken x here. So this will write x is equals to C1, U1 plus C2 or C1, sorry, I have taken some other this here. So I should go according to this. This is, I should not take them u, v, and w. Just we will stick to the notations which are used here. What we do is, say these three vectors are given to you. I'm not naming them. And this spans R3 because any vector in R3, any vector, any arbitrary vector u can be written as a linear combination of these vectors. So you have to write u as a linear combination C1, 1, 0, 0 plus C2, 0, 1, 0 plus C3. This is the linear combination of the vectors. You have already studied this. And if we are able to write any arbitrary vector u which is inside R3 as a linear combination of these vectors, then we will say that this set S spans this R3. Now, for checking whether you can write this u as a combination of these vectors, you will need to find out some finite values of C1, C2, and C3. Okay, so if you just write u here, u has the components u1, u2, u3. And here, if we take C1 inside, then add, do the scale, this is scalar multiplication, and then do the vector addition. We will get here C1, C2, and C3 because C1 will go here. This becomes C1. First component of second is 0. It's also 0. So C1 plus 0 will give you the first component at C1 here. Similarly, you will get C2 and C3. Now, if you compare both the sides, you will get U1 equals to C1 or C1 equals to U1, and then C2 equals to U2 and C3 equals to U3. So this gives you the values of the scalars here. Then if you put these values of the scalar here, you will see that you are able to write u as u1 into 1 0 0 plus u2 into 0 1 0 plus u3 into 0 0 1. So you can say that any arbitrary vector in R3 can be written as a linear combination of the vectors in S. So S spans this R3. Similarly, we have another example. You can go through it also. In this case, we have to again show that the given set of vectors here, this given set of vectors, this spans R3. Previously, we were having the vectors 1 0 0 0 1 0 0 0 1, but now we have these vectors, another vectors. Now, how we will check this, whether this S spans R3 or not? Again, we will take some arbitrary vector u inside R3, okay? And then we will try to write this u as a linear combination of the vectors v1, v2, v3. And if we are able to find out the values of c1, c2, c3, if we write this linear combination like this, we try to write any arbitrary vector in R3, which is u, as a linear combination of these vectors, which is c1, v1 plus c2, v2 plus c3, v3. And if we are able to find out some finite values of c1, c2, and c3 here, then we will say that we are able, this S, the given set S spans the vector space R3. So the above problem thus reduces to determine whether this system is consistent. So I hope you might have studied this, how to find this linear system of equations, how to solve this linear system of equations. For that, if your right hand side is unknown to you, u1, u2, u3, either one way is whether you find c1, c2 or and c3 by solving these equations. You may get their values in terms of u1, some combinations of u1, u2 and u3. Okay, this c1, c2, c3 you will get as a combination of u1, u2, u3. That means their values you will get in terms of u1, u2 and u3. If you are able to get that, then we say that okay, we can write u in this form by putting the values of c1, c2 and c3 in terms of u1. As in the previous example, you got the values of c1, c2 and c3 as this u1, u2 and u3 only. Similarly here, if you solve this system of linear equations, you will get the values of C1, C2 and C3 in terms of U1, U2 and U3. And another way is to check whether you get some solution in between these equations is not, because it may happen that these three equations are not solvable. Okay, that means there exists no solution among this system of linear equation. That also may happen. In that case, S will not span the vector space R3. But for checking whether we will get some solution among them or not is to find out this determinant of the matrix A. How you make the determinant of matrix A, this you might have already studied, that if we write this linear system of equations in the form A into x equals to B. Okay, B is the right hand side vector. You will write it as a vector as u1, u2, u3, and similarly your vector x is the vector c1, c2 and c3, and A is nothing but the coefficients here, that is written as 1 0 minus 2 2 1 0 3 2 1. This you might have studied already, how to solve this system of linear system of equations using the matrices by writing in this form Ax equals to B. In the simple form you have studied, if we get this determinant of A not equals to 0, then we say that this we have a unique system, a unique solution among the given system of equations. Okay, so this here what we do is we get this determinant of matrix A and we are getting it not equals to 0. So it shows that there is a unique solution existing among the given set of linear equations. So Ax equals to u has exactly one solution for every u, because determinant of A is not equals to 0. And that solution you need not to find here, because you are not asked to find the solution. You have to just check whether the given set spans R3 or not. So if we are able to get the values of C1, C2, C3, which are the unique values in terms of U1, U2, U3, then we will say that the set S spans the vector space R3. So that is what we got here. Now, next we come to the linear independence. And associated with linear independence is its opposite, that is the linear dependence. So first, let me tell you what is the linear independence. Say you have been given a set of vectors S. In this set of vectors, we have the vectors k vectors v1, v2, and so on vk. This is the given set of vectors, a set of vectors in a vector space V. So this set is inside the vector space V. Then if we write the linear combination of these vectors inside S as C1 V1 plus C2 V2 plus CK VK, and we put it equals to the zero vector, and if this linear combination, when we put it equals to zero vector, this has only trivial solution. Trivial solution means the values of all these scalars is equals to 0. That is called the trivial solution. If we get a trivial solution only for this, then this set of vectors v1, v2, vk is called a linearly independent set of vectors. Or we say that these vectors v1 up to vk are the linearly independent. And if the equation has a non-trivial solution, that means you get some non-zero values for some of the scalars here, C1, C2, Cn, Ck may say in between C1, C2, Ck. Among these scalars, if you get some of the scalars which does not have the value equals to 0, then we say that this set of vectors v1, v2, vk is linearly dependent. So linearly dependent is just opposite to the linearly independent. So you will just how we will find it? We will be given any set of vectors S. We will write their linear combination. Linear combination, you know how to write by choosing some arbitrary scalar C1, C2, Ck, writing this combination C1, V1 plus C2, V2 plus Ck, Vk, and putting it equals to zero vector. Now this zero vector is what? This zero vector will be according to what is this those vectors Vk here. If those vectors Vk are in the k dimensional space Rk, then they will have the components. Let us say V, that will have the components V11, V12, and so on up to V1k. Similarly, all the vectors will have k components, and so this zero vector will also have the k components here. 0, 0, 0 up to k0 will be here. Okay, and if you just put them equals to this zero vector, then you should be able to get the values of all these scalars C1, C2, Ck equals to 0. And in that case, our vectors will be linearly independent. If we are not able to get all these scalars equals to 0, any of them is non-zero or all of them are non-zero, then we will say that the set of vectors is the linearly independent set. Now we'll have one example here, how to check the given set of vectors is linearly independent or not. So let us say, determine whether the following set of vectors in R3 is linearly independent or linearly dependent. This Li means linearly independent, LD means linearly dependent. So this S is given to us where V1 is 1, 2, 3, V2 is 0, 1, 2, and V3 is minus 2, 0, 1. We have to check it to be linearly independent or dependent. So what we scale and do the scalar multiplication and afterwards do the vector addition, and then you will get, by comparing the left and the right hand side, there will be three equations formed here. There are three equations in three unknown again. Now we have to check what is the value of C1, C2, C3 you get here. So if you solve these equations either using that matrices form or by directly solving the equations, you will get the values of C1, C2, and C3 to be equals to 0. Okay, so that means there exists only a trivial solution among the scalars, and so our V1, V2, V3 are the linearly independent set of vectors. So this is very important, the linear independence for you people. So it should be very clear to you whenever you are asked to find whether the given set of vectors is linearly independent. First you will find its linear combination and put it equals to 0. Then all in this linear combination, all of your scalars should get the value equals to 0 finally. And if it is 0, then the set of vectors is linearly independent. Why this word linearly independence and linearly dependence arose is because you have three vectors. Let us say we have three vectors u1, u2 and u3. These three vectors you are having. Then the meaning of linear dependence of these vectors is that any of the three vectors will be written as a linear combination of other two vectors. It may be u2 equals to c1 u1 plus c2 u3, or it may be equals to u1 equals to c1 u2 plus c2 u3, okay, or maybe u3 equals to c1 u1 plus c2 u2 for any number c1 and c2 here. So if one of the vectors from the among the given vectors can be written as a linear combination of other vectors, then we say that the vectors are linearly dependent upon each other. That means there is a dependency of one of the vectors upon the values of the other vectors. But if we are not able to write any of the vectors as a linear combination of other vectors, then we say that the vectors are linearly independent. Okay. Next, we have the basis and dimensions. According to this linear independence and dependence and the spanning sets, we will get the basis and dimension of the vector space V. Let us say V is a vector space and you have some set of vectors S, which is in which we have the vectors taken from the vector space V. This was your vector space V. In this vector space, so many vectors are there. You have taken some of the vectors. This vector is the n-dimensional vector space, or you can write it as Rn. You have taken n vectors from this vector space. These are the n vectors, say u1, u2, and and up to so on un. N vectors we have chosen from this vector space, and we have given that set and the name capital S. So capital S is a subset, or it may be equals to V. And we say that this set of vectors S spans V. Spans V means any other vector inside V can be written as a linear combination of these n vectors only. Okay, this was your set S. So we will say that S spans V. And the second thing, that S is linearly independent. If these two properties are satisfied by this, then this S is called a basis for vector space V. So what is the meaning for basis for vector space V is, from this set S, we can find out any of the vectors of this vector space V with the property that it is also a linearly independent set. So if the given set is linearly independent and also any of the vectors we can get by finding the linear combination of the vectors inside the S, then S will call the basis of the vector space V. So basis S must have enough vectors to span V, but not so many vectors that one of them could be written as a linear combination of the other vectors in V. What does it mean? It means that it should not be that it can be written as a linear combination of other vectors in V. That means it should not be linearly dependent. It should be linearly independent. So if it spans V and it is linearly independent, it is the basis set for the vector space V. This is the basis. Now we have some standard basis for the given vector spaces. For any vector space, the standard vector space is, let us say, if you have R3, the standard vector space for this will be, in the first vector, the identity or 1 at the first position and other positions are 0. Similarly, for the second vector, there is one at the second position and others are zeros. For the third vector, the one at third position and other vectors are zero. This is the standard basis for the R3 or the vector space in three-dimensional. Okay. Similarly, we can have the standard basis for Rn, n-dimensional vector space. In this case, we denote them with E1, E2, and En. Because this is an n-dimensional vector space, its basis will have n vectors here, E1, E2 up to En. In case of E1, there will be one at the first position here. In case of E2, this one will be at the second position. In case of En, this one will be at the nth position. So this kind of this vectors, that is the basis for the vector space of dimension n. As it is given the example for four-dimensional vector space also, R4 you can see here. Now, not only we have the standard basis for any n-dimensional vector space, we can have some other non-standard basis also for the given vector space, as is the example here. Here we have the non-standard basis for R3, but we have to check whether the given this set of vectors, let us see you have been given this set of vectors, which is having the vectors 1, 1 and 1, minus 1. You have to check whether this is a basis for R2 or not. For that, you will have to check whether this set of vectors spans R2, and also you have to check whether this set of vectors is linearly independent or not. So there are two conditions to be checked, whether the span of S is a spanning set for R2 and whether the set of vectors S is linearly independent or not. If these two conditions will be satisfied, then we will say that this set of vectors S that spans the vector space R2. So this is a basis for R2 also. Now, uniqueness of basis representation is, if S is a basis for a vector space V, then every vector in V can be written in one and only one way as a linear combination of vectors in S. What does it mean is, you can have the standard basis for a vector space, you can have some non-standard basis also for the vector space, but whenever you have a basis, in any basis, if you have a vector space of n-dimensional, then in that basis set you will have n vectors, and in all the bases you will be having n vectors, let us say v1, v2 and vn. So these vectors may change, but their quantity will remain same. That means there will be only n vectors in the basis of an n dimensional vector space Rn. Then basis and linear independence. If S is a basis for a vector space V, then every set containing more than n vectors in V is linearly dependent. As I told you, that if you are having n vectors in a basis, that will be linearly independent. If you have more than n vectors in some set, then those will be linearly dependent. And if a vector space has one basis with n vectors, then every basis for V has n vectors. This I already explained you, that whenever you may have the standard basis or you may have the non-standard basis, but in every basis the number of vectors will remain the same. So if this is an n-dimensional space, there will be n vectors, 1 to n, and if this is a four-dimensional vector space, you will have four vectors, v1, v2, v3 and v4 in every basis of this vector space. So every basis will have the same number of vectors in it. Okay, then the dimension of a vector space V is defined to be the number of vectors in a basis for V. And a vector space V is called to be finite dimensional if it has a basis consisting of a finite number of elements. If the basis consists of a finite number of elements, then the vector space V is a finite dimensional vector space, as it is, let us say, Rn. And if a vector space V is not finite dimensional, then it is called the infinite dimensional vector space. Next, we have these things we have already studied, that if you have in a vector this V, vector space V, if you have some spanning sets, which is linearly independent set also, then that will form a basis for the vector space V. and as many number of vectors are there in the basis basis of vector space V, that will give you the dimension of this vector space V. So that is equals to n in this case, if the number of vectors in the basis are equals to n. So find the dimension of vector space according to the standard basis. The standard basis for Rn, we have E1, E2 up to En, and every vector is having n number of elements here, and there are n vectors here which form the basis for the vector space Rn. So the dimension of Rn is written as equals to n. This n written as a superscript here that denotes the dimension of the vector space, and it is written as dim of r to the power n, which is equals to n. Dimension of Rn is equals to n here. Okay, so with this vectors is complete. Next we'll move towards the matrices. So this is a long part because we don't have so much time. I think I should tell you these things in short. So here I'll explain you what is the rank of a matrix and how to find the nullity of a given matrix. Rank and nullity are very important concepts in terms of the matrices, and we will just find the rank and nullity in terms of the vectors only. So there are so many ways to find the rank and nullity of a matrix. We'll choose one of them, and that the thing which we are choosing is actually related to the vectors. So in terms of the vectors, how we find this rank and nullity, let me tell you. Let us say you have been given this matrix A, and you are asked to find what is the rank and what is the nullity of the matrix. So for that, you will need to find the row echelon form of this matrix. So first, let me explain you what is a row echelon form and what is a row reduced echelon form of a given matrix. And then the concept of rank and nullity will be more clear to you. Here we have a rectangular matrix is in echelon form. There are two things, echelon form and or called the row echelon form. And another thing is the row reduced echelon form. We have two terms, row reduced echelon form, or in some books it is also written as reduced row echelon form. So anyway, that is the same thing. First, let me tell you what is the echelon form only, or the row echelon form. The row echelon form of a matrix is if the matrix is satisfying these four conditions. That is, all non-zero rows are above any zeros of a matrix. So I will give you one example here by writing this matrix 1 0 0 2 1 0. One more I will take here, that is 0 0 0 0. Now let us say we have this matrix, and I say that this matrix is in the row echelon form. Then it should satisfy these properties that you will check. If I tell you that this is in the row echelon form, then you will try to check whether I am saying correctly or not. For that, you will have to check these properties. The first property is that all non-zero rows are above any rows of all zeros. That means all the zero rows should be the last rows. So you will see that we have a zero row here. This is the zero row, and it is in the end of this matrix. Okay, all the non-zero rows are above the zero rows. Second is each leading entry of a row is in a column to the right of the leading entry of the row above it. That means whatever row we go, if its first non-zero entry should be after all the zeros in that row. That means here this is the first non-zero entry. Before it we don't have anything, so it's okay. Then we go to the second row. Whatever is the non-zero entry here, that which is called the leading entry, the leading entry of a row is in a column to the right of the leading entry of the row above it. So if you see the leading entry of the row above it, then it should be in the right of that leading entry. So as you see here, The leading entry of the first row was at this position. Then the leading entry of the second row is in the right of this leading entry. Similarly, if we go for the third row, where is the leading entry of this row? After all the zeros, the first non-zero element is called the leading entry. So in this third row, the leading entry, if we go towards it, this is the first leading entry and it is in the right of the leading entry of its previous row. That is here. And if we go to the fourth, it does not have any leading entry because all the zeros are here. So this is the last row here. Then all the entries in a column below a leading entry are zeros. So if we look at the leading entry point here, for the first row, all the entries in the particular column should be zeros. So whatever is the leading entry we have here, all the elements in that column should be zero. This is the leading entry of the first row. If we go to the second row, the leading entry is this one here. And all the elements in this column below this one are zeros. Similarly, this is not the leading entry, so we will not look up at this. We will go to the leading entry of the third row now. This is the third row. The leading entry is this one. And all the entries in this particular column are zeros here. So this is called the row equivalent form. Now, what is the row reduced equivalent form? In the row reduced equivalent form, you will see that you should also have zeros above the leading entry point here in all this. So if this row equivalent form is reduced to the row reduced equivalent form, if we write it as like this, whatever is the leading entry in the second row leading entry is this one. Above and below at all the positions, there should be a zero in this case. So that third element, that is not the leading entry. So we will not take care of this. It can be anything. Then the third, we go to the third row, the leading entry is this one. So above and below this third leading entry, all the entries should be zero. Then this is called the row reduced equivalent form. So some people use row reduced equivalent form. This is according to the situations. If we are trying to solve the linear system of equations, we may need to use the row reduced equivalent form. But for finding the rank and nullity, we don't need to go for the row reduced equivalent form. Finding the row equivalent form is itself sufficient. But it should be clear to you that now, if we have this row equivalent form, we make a staircase here with the leading entries. Okay, if you go to the first row, this is the leading entry. It should be at this point for the stair. Then we make the second stair here. This staircase, we will go to the second row, and this will be at the joining point of this. This is the first leading entry, and this two will not take care of. This will come inside this step only. And then we will go to the third leading entry by making a cross this here, like this staircase here, and this gives you this kind of structure. Okay, so we can take another example also here. Say we have 1 0 0 0 2 1 0 0, then 1 2 3 1. Sorry, 1 2 3 and 1. So how we'll make the staircase here? This, and now this is not in the row equivalent form. If you write like this, so you will have to change it and make it 0 by multiplying this with the 1 by, if you multiply the third row with 1 by 3, and then you can make a 1 here by multiplying with 1 by 3, and so your step case will be like this. So this is now in the row equivalent form. I hope this row equivalent form is clear to you. Now in our case, the first thing to find the rank and nullity is to reduce the given matrix in the row equivalent form and look at the staircase which you have made here. In this staircase, if there is a single entry in this stair, then that means the vector corresponding to this I will explain you again here like this by taking one example. As we have taken here 1, 0, 0 and 0. Then you have 2, 1, 0, 0. Then we have 3, 2, 0, 0 and 1, 2, 1, 0. It is not written very neatly. Now, each of the entries of any matrices, this is a matrix. Each column of this matrix that represents a vector here. Okay, so that is why vectors and matrices are very closely related. Each entry of the matrix we can consider as a vector. Let us say this is the vector u1, this is your vector u2, vector u3 and vector u4. Now, when you reduce the matrix in the echelon form and you make a staircase like this by making the leading entry 1 using the row operations only. Okay, you have to take care that when you are reducing the matrix in the row echelon form, you will use only the row operations. The row operations are adding two rows together, multiplying any row with a number. That means adding two rows, say row R1 plus row R2, multiplying any row with a scalar, okay, and then multiplying any row with scalar and adding to the other row. These are the standard row operations. With the help of these standard row operations only, we reduce the matrix to the what? Row echelon form. And when this is reduced to the row echelon form, then what you do is you will just make the staircase by these and leading entries, which are called the pivots also, in the step case like this. Now we are going to the second row, because in the second row the first and non-zero entry is 1, so this will be the only leading entry of this, and the other entries will go in the same step here. Then we'll make the another step for the third row, and the fourth row is not having anything. This is here. So you see that if you look at the vector v1, this is having only one leading entry, and in this step there is no other number. So this is the, we will mark this vector u1 vector. Then if we go to the second vectors, it is having, in this step we are having two numbers, number 1 and number 2, but its leading number is this one. So this vector also we will mark, this u2 vector, and we will leave this second vector which is on the same step of this. Then we will go to the third vector here, this third step here. In the third step we are having only one entry, which is the 1, and this corresponds to the vector u4. So all these vectors which corresponds to the this leading entry here, which is the pivot element also, it is also called the pivot. In some books it is written as the pivot element. So these vectors which corresponds to the pivot elements, those vectors are said to be the linearly independent vectors among the given vectors. So here inside the matrix A, you had four vectors, u1, u2, u3 and u4. But among these four, only u1, u2 and u4 are your linearly independent vectors. And this vector u3 is dependent on the other three vectors. It is dependent on u1, u2 and u4. Okay, so this is the way of finding the linearly independent vectors. Now, how these linearly independent vectors are related to the rank and nullity? Let us check out how the vectors are related to the rank and nullity. With this example, we will see. Let the column vectors of this matrix A, as they are denoted by this A1, A2, A3, A4, A5 here. This is your first vector, A1, second vector, A2, then third vector, A3, A4 and A5. And this matrix is of the order 4 by 5. Now we have to find the rank and nullity of A. So what we do is, first, what we do is we just reduce this matrix to the echelon form. When you reduce the given matrix A in the echelon form, you will get the matrix B. And here you see that if you want to make the steps, this is the first step. Then you go to the second step. In the second step, we have two entries, 1 and 3. Where then we go to the third step. Third step also we have two entries here, 1 and -1. Now these are the new vectors b1, b2, b3, b4 and b5 they have written. Now how would you check which of the vectors are linearly independent here, which are having the leading entries on each step? So this vector, that is vector b1, then this vector b2, next our vector b4. Only these three vectors are linearly independent. The other two vectors b3 and b5 are dependent upon these three vectors b1, b2, b4, and correspondingly you will check what are the original vectors there. This is the row reduced form, and in the original we were having the corresponding vectors a1, a2 and a4. So we will say that our given vectors a1, a2 and a4 are linearly independent. So the rank of the given matrix will be the number of linearly independent vectors in the given matrix. So the rank of this matrix A is equals to 3. And according to the rank and nullity theorem, we have a very important theorem which is called the rank nullity theorem. According to the rank nullity theorem, the rank of a matrix plus the nullity of this matrix is equals to the number of column vectors. Number of column vectors. So how it is related to the data sciences, let me tell you. In the data science, you represent the data in the matrix form, and in this side, in the rows, we have the samples, and in the column side, we have the attributes. So all the columns represents the attributes, and all the rows represents the samples. So in case of the attributes, if you want to find out which of the some of the attributes may be some combination of the other attributes, so they may not be useful for us. So for finding those non-useful attributes, we will make use of the nullity here by first finding the rank and then by using the rank plus nullity theorem. Rank nullity theorem says us the rank plus nullity is equals to the number of column vectors. So in this case, we got the rank equals to 3, which was the number of linearly independent columns, plus nullity we have to find out, and this is equals to the number of columns. How many number of columns were there? 1, 2, 3, 4 and 5. So from that we get nullity is equals to 5 minus 3, that is 2. That means there are two vectors which are not useful for us because they are the linear combinations of the other three linearly independent vectors. So this is how you find out the rank and nullity, and this is how this rank and nullity is useful for the data science people. And that is all with this. Thank you, everyone.
Okay,
if you have any queries, can be asked.